So the title of my PhD thesis is called Quadrotor Fault-Tolerant Flight Control and Aerodynamic Model Identification. So as we know that the quadrotors are very popular nowadays thanks to their relatively lower cost and the structural simplicity compared with a normal helicopter. So they have been widely used in many fields such as filming, agriculture, power line or infrastructures, inspections, and in the near future we can also expect more drones operating in the air and delivering the packages even above the urban area. But the prerequisite of all these applications is that these drones, they must be safe. So from this video you can see that this skier was almost killed by a big quadrotor which loses control. And actually we can also see many other reports showing that the drone crashed to the ground and harming persons and infrastructures on ground. Therefore, the focus of this thesis would be a very specific type a very specific threat to the safety. We call it motor failure. So if one propeller if the quadrotor loses one propeller, as what is shown in this video, you can see that the drone is very easy to crash. Actually, this rarely happens nowadays, but we can expect that in the future when tens of thousands more drones are operating in the air, and this must be a major concern. And the method we used in this research is called fault-tolerant control algorithms. So since this is only algorithms, therefore we only need to adapt the software on the drones, and it would be more lightweighted and cleaner than simply adding parachutes or adding redundant rotors. So therefore, there are many pieces of research trying to address this problem. And here in this video is a very famous one from Mueller and Danlia. And you can see that from their research, and they prove that a quadrotor is even flyable after a complete failure of a single propeller. However, the problem of the state-of-the-art approach is that it's relying on a very accurate mathematical model of the quadrotor. But in reality, there will be a lot of unknown effects such as aerodynamic effects, and these aerodynamic effects can be very significant and will cause a lot of model uncertainties and will make the current FTC fail. And here I draw a plot to show the related works about the Quadrotor FTC. It's not all the literatures, but just to show some very important literature here. We can see that the vertical axis here indicates the level of failure from no failure to the complete failure of a rotor. And the horizontal axis shows the amount of model uncertainties. So we can clearly see that what is missing now is on the top right corner, where a complete failure of a rotor happens, plus a significant aerodynamic effects, causing a massive model uncertainties on the current flight controller. So therefore, this part would be the goal of this work, to design a robust fault-tolerant flight controller to be resilient to these significant aerodynamic effects. To this end, I have conducted several sub-projects. So the first projects, what I did is that I identified the quadrotor aerodynamic models in the high-speed flights. This is because before designing a fault-tolerant controller, we need to further observe and understand and even model these high-speed induced effects. So therefore, I have conducted several wind tunnel flight tests of a quadrotor in the OpenJet facility of TU Delft. We can see that in this wind tunnel, we can change the flight velocity from 0 to the maximum speed of the drone at around 16 meters per second. We can also change the hovering angle of the drone and even control the drone to track certain waypoints. So by analyzing the flight data obtained by the IMU, onboard IMU, and the offboard external motion capture systems, we can observe some high-speed induced aerodynamic effects. For example, we can observe a linear aerodynamic drag with respect to the air velocity, which is different from the aircraft, which usually having this quadratic aerodynamic effects, aerodynamic drag. And we also observe a significant pitch-up aerodynamic model in the forward flight. And as a consequence, we can find that the rear rotor of the quadrotors need to spin much faster compared with the front rotors of a quadrotor during the forward flight. We also observed a massive aerodynamic induced yaw moment, especially in the large side slip angles, and we suspect that this is because one rotor is within the wake generated by the fuselage. So after observing these aerodynamic effects, well, there are also some other effects, but I didn't show them here. But okay, and then we can use this flight data and then leverage this stepwise regression algorithm to identify a gray box model. And this gray box model will predict the three-axis aerodynamic forces and moments acting on the entire quadrotor. And here is an example showing the validation results of the pitch moments on the entire quadrotor. We can see that this plot compares the measurement, the gray box model, and a benchmark hovering model. We can clearly see that the gray box model outperforms this hovering model a lot. Afterwards, with the aerodynamic model identified, we can also establish a 6 degrees of freedom simulator. And this simulator would be beneficial for the next step to design these fault-tolerant flight control algorithms. And that is the second project, to design a robust FTC for high-speed flight of a quadrotor, despite loss of a single rotor or two opposing rotors. So before we dive into the FTC, we can first look into how a quadrotor controls itself. So for a normal quadrotor, it uses 4 control inputs, and in order to control 4 channels. And these channels are the collective thrust, the pitch, roll, and yaw. However, if one motor fails, we cannot fully control these 4 channels. And a very straightforward strategy is to simply abandon the yaw control, such that the collective thrust, the pitch, and the roll channels are still fully under control. But the consequence is that the drone will faster spin, and the spinning rate would be about 3 to 4 revolutions per second. And here I used the so-called reduced attitude control to only control the thrust direction instead of the full attitude of the quadrotor. And then I asked the thrust direction to track a certain designed direction. And here is a general control diagram of the proposed control algorithm. So for the outer loop, we use a PID controller to track the certain waypoints. And for the middle loop, I use the above-mentioned reduced attitude controller. And the key is the inner loop. So for the inner loop, we use a incremental nonlinear dynamic inversion controller, or INDI. So this control methods it uses the most recent sensor measurements to replace part of the information of the model. So therefore, it has very high robustness against the aerodynamic disturbances. So thanks to the INDI, we can conduct the wind tunnel flight test of the drone in the wind tunnel. You can see that now the drone is hovering in the wind tunnel at about 6 meters per second. And after several seconds, we'll simply switch off one propeller. And you can see that the drone will start fast spinning, but it is still able to control itself despite this large aerodynamic effects, and finally even navigate back to home. So in this video, we further test the robustness of the proposed FTC algorithm. So we asked the drone to hover in the wind tunnel, and we gradually increased the wind speed until the drone crashed. You can see that the drone will finally crash until the wind speed reached above 9 meters per second, which is already more than half of the maximum flight speed of a drone in the normal case, which was about 16 meters per second. So for the next step, I generalized this INDI inner loop flight controller from the single rotor failure condition to a double rotor failure condition. And this would be challenging for the INDI, so I made some theoretical improvement. And here I use a output redefinition technique where I define a new output, and here this new output y2 is scheduled by a parameter called chi. And we can prove that with a good selection of chi, we can still make sure that the drone with double rotor failure is still stable. So for the next step, I validate the drone with double rotor failure, also in the wind tunnel. And this time I made comparisons with a benchmark LQR controller. So for the first comparison, we tested the maximum flight speed of both methods in different selection of gains. We can clearly see that the INDI controller outperforms the LQR in terms of the maximum speed, and the improvement is about 50%. And then I also asked the drone to conduct a trajectory tracking task in the wind tunnel under a wind speed at about 5 meters per second. We can see that this LQR controller failed while conducting a crosswind maneuver, while the INDI controller is still able to finish the whole track. All right, so now we have already obtained the data in both nominal flight condition without failure and the flight condition with failures. So we can further improve the aerodynamic model we have identified in the first project. So we find that this model is improved and is able to even predict some effects that is only observed in the rotor failure condition. So for example, here, Quadrotor is flying in the wind tunnel and is fast spinning. We can observe a lateral force that is perpendicular to the flight direction. And this lateral force actually, it's linearly increasing with the flight speed, and the direction of this lateral force is also decided by the spinning direction of the quadrotor. We can see that the proposed model in red can perfectly predict this lateral force, whereas a benchmark model cannot. So here we use a lumped parameter benchmark model, which have been widely used in the community. But please note that here, the parameters are also identified from the flight data. So it shows that the advantage of the model structures that I'm using. So apart from the rotor failure condition, this model is also able to predict the quadrotor trimming curve in the no failure condition. So when the drone is flying forward, and because of the airflow, and we can see that the pitch angle, the RPM of the front rotors and RPM of the back rotors, they're changing with the flight speed. And our model is able to fit this trend very well, while the benchmark model cannot. Okay, so now let's come to the next project. So until now, we assume that the drone will enter this fast spinning motion right after the failure happens. But in reality, and this is not the case, because there might be a delay caused by the fault detection system, or because of the drone collision with other drones. So when the drone realizes that it loses one rotor, it perhaps already entered an upside down orientation. So therefore, the goal of this project is to design a post-failure recovery algorithm to help the drone to recover from this upside down orientation. And so what I did is that I revised the original control allocator, and I add a simple envelope protection constraint into this control allocator. And this envelope protection constraint can help the drone to recover much faster. So from these two videos, so both drones, they are initialized at an upside down orientation and with a very, very high angular rates, which is very hard to recover. So from the left-hand side, you can see that without this protection constraint, the drone will keep falling until it crashes. But on the right-hand side, with this protection constraint, the drone is able to recover before falling by 3 meters. We also test this recovery algorithms in the real flights. So in real flights, we just randomly throw the drone into the air to create this random initial orientation and angular rate. So you can see the drone could easily recover before crashing to the ground. And we hope that this method can further improve the drone safety in an even more realistic scenario in the future. Okay, now come to the last project in my PhD thesis. So in the last project, I conducted onboard, so I use onboard vision sensors to provide state estimates for a quadrotor fault-tolerant control flight. And this project is in collaboration with the robotics and perception group from University of Zurich. So, for most researches about the fault-tolerant control, and we use these external vision sensors or motion capture systems to provide the position and the velocity estimates of a quadrotor. However, in reality, the drone needs to rely on the GPS, or in some GPS degraded environment, it may fully rely on the onboard vision cameras. So the question is, can a quadrotor use only vision cameras, using only onboard cameras to conduct fault-tolerant flight control? Well, the answer is yes. So in this video, we can see that the drone is flying with only 3 propellers, and there is a downward watching camera, downward facing camera, to provide the position estimates of the quadrotor. And from the right-hand side is the raw frame of the camera and the features detected. We can see that with this camera-based state estimation, the drone is able to conduct forward and backward flights, track a trajectory, and eventually conduct a safe landing. Okay, now comes to the conclusions and outlook. For conclusions, first of all, I designed a set of fault-tolerant control algorithms that are robust to significant aerodynamic effects in the high-speed flights, and we have validated in the wind tunnel flight tests. Secondly, we observed a lot of high-speed induced aerodynamic effects of a quadrotor and identified their models. We also designed upside recovery algorithms for quadrotor post-failure conditions. In the end, I designed and validated a vision-based state estimator for quadrotors to conduct autonomous flight despite rotor failures using only onboard cameras. And here are some outlooks and recommendations. So first of all, since in our research, only this, we use a phenomenological approach to identify this aerodynamic model, but we cannot explain the underlying physical principles behind these aerodynamic effects. So therefore, the first recommendation is to do more research, try to review the physical principles behind these effects, and this would be very helpful to improve the accuracy of current model and even generalize it to other UAV configurations. And secondly, the INDI flight controller in our research, it neglects this actuator dynamics, and we find that it will cause some performance degradation in our test. So therefore, it is recommended to design actuator dynamic compensator in the future research. Third, it would be also interesting to see how to fuse different sensing modalities like GPS and onboard cameras, the barometers, magnetometers, etc. on quadrotor in these rotor failure conditions, and then make comparisons with the condition without any rotor failures. And in the end, we also recommend to do more research to generalize the current FTC algorithms to hybrid configuration UAVs. Okay, thank you very much for your attention to this presentation. And if you have further questions, please feel free to contact me via this email. And the public defense will start in around 10 minutes at 6 p.m. Thank you very much.